Hello everyone, a very good morning, afternoon, and evening to all. Dear authors and invited guests, welcome to Technical Session 7B. Myself, Anisha, and this session would be moderated by me on behalf of Global Knowledge Research Foundation and GR Scholastic LLP. It is my great pleasure to welcome you all to the 9th World Conference on Smart Trends in Systems, Security and Sustainability, WS4 2025, London, UK. The ninth edition of the conference is being organized in a hybrid mode. The physical event was held in London, UK on 19th of August 2025, and the virtual event was held yesterday and is being held today through Zoom, that is 20th and 21st of August 2025. I hope you all will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations, and each presenter will be given 12 minutes for the presentation and 3 minutes for question and answers. On 10 minutes, I'll be raising a gentle reminder. There's another request to all the participants that you all please stay connected with us till the closing of the session. And if you have any update or query, you can write it down in the chat box. So just before we start the session, I'd just like to introduce you all to the chair for this session. Firstly, we have Dr. Rizal Abdul Qadir. He is a senior lecturer at Universitas Islama Riyadh, Indonesia, a senior member of IEEE and a member of ACM. His research interests include software quality, models and architectures, software measurements, information systems, software engineering, machine learning, information cybersecurity, and e-systems. We welcome you to the session, sir.
Hello, yes, Anisha. Thank you.
And we have another session chair with us, Dr. Praveen Chopala. Dr. Praveen is a professor in the Department of Electronics and Communication Engineering at Andhra University, India. He also serves as the chairman of the Board of Studies, UG Electronics at the university. His research interests lie at the intersection of signal processing, machine learning, and Bayesian estimation, with applications spanning engineering, biomedical sciences, and economics. We welcome you to the session, sir.
Yeah, thanks, Anisha, and welcome all.
So now we'll be starting off with the presentations, and we have our very first presenter, Matthias, with the paper titled A Hybrid Differential Evolution and Reinforcement Learning Approach for Optimizing Convolutional Neural Networks in Facial Age Group Classification.
Thank you. Good afternoon. I'm Omatayo Oladede from Federal Polytechnic Ede. I'm presenting the paper titled A Hybrid Differential Evolution and Reinforcement Learning Approach for Optimizing Convolutional Neural Network in Facial Age Group Classification. Yeah, these are my presentation outline. The introduction, the research motivation, model formulation, methodology, results and discussion, the comparative performance, fairness evaluation, conclusion, then some references. The introduction, facial age classification has emerged as an important task in computer vision and is targeted towards approaches such as targeting, advertisement, access control to social media analytics, and human-computer interaction, according to Singh and Texi. Fortunately, there has been good process through deep learning, particularly convolutional neural network. But unfortunately, despite the high accuracy of this model of these approaches, there still remain a challenge. And this challenge includes variations in facial features, lighting conditions, and demographic diversity. Then these are the challenges, and that was what motivated us into this research. Under-representation of black faces in the training dataset, then variations in skin color and distinct facial features, and poor generalization of conventional models. Then the following ethical concerns are also part of what prompted us into the research. These include biased predictions and reduced accuracy, fairness and inclusivity issues in AI, and the need for equitable facial analysis systems. And to address these challenges, a CNN algorithm optimized with an hybrid differential evolution and reinforcement learning was developed. Then this is hybrid differential evolution approach, DRL approach. Differential evolution is a population-based meta-heuristic algorithm that has the global search ability and is capable of exploring different training architectures and hyperparameter configurations, which is a challenge in convolutional neural network. While reinforcement learning is a dynamic learning mechanism that adjusts model behavior based on performance feedback, enabling fine-tuning throughout the training process. And the combined strength of these two initiates a search for optimal CNN architecture, while RN defines the learning process by rewarding configurations that yield higher classification accuracy. D initiates a search for optimal CNN structures. Then the data set and preprocessing. The dataset that was used in this research include the UTK phase dataset and the KCR phase Africa dataset. The UTK phase dataset, the black images there were used and not the whole images, while the KCR phase Africa is majorly for black faces. Then 900 images were selected using stratified sampling. The choice of the selection is because of the images low representation were selected and as such to reduce overfitting to solve the problem of imbalanced data handling. Then uniform distribution across 9 age categories and to encourage balanced representation for fair evaluation. The preprocessing includes face detection using the DLib HOG's histogram of gradient based face detection. Then the face alignment with landmark detection was also done by DLib. Then the image was normalized and augmented. Then the noise were reduced using median filtering and the images were enhanced using histogram equalization. The model formulation. The population size of 16 was chosen and 5 generations. This was to balance exploration and computational efficiency. As data set that was used were just 900 face images, and the transfer learning was used VGG16 for the model. Then the hyperparameter space. These are the hyperparameters that will optimize the learning rate, the dropout rates on closing layers, and the batch size. And the learning rate was between 1e raised power 5 to 1e minus 3. The dropout rate was between 0.3 to 0.5. The closing layers include 0, no closing layers, 4 closing layers, and 8, while the batch size ranges between 8, 16, and 32. Then the DE operations. A mutation factor of 0.6 and crossover probability of 0.9 was chosen, and this was to explore the hyperparameter space. Then for the RL component reinforcement learning, 5 discrete actions was performed. We had to decrease or increase or add noise, push from 0.5, and random reset. These were used for the reward and the penalty. Then this is the flowchart of the model, of the developed model. The DE populations and RL agents were initialized. Then after it was trained on a CNN on the current population. Then the fitness and that is the validation accuracy which was used for the fitness was evaluated. And at the end of the day, we tested if the parameter was adjusted by the reinforcement learning agent. If it was adjusted, it's going to update the D parameters, then run the training again. If no, it's going to proceed with the current parameters, differential evolution parameters. Then it's going to check if the maximum generations have been reached. If it has been reached, it's going to select the best individual. If no, it's going to go back and retrain again. Then, after selecting the best individual, the final training will be performed with the best individual, and the model will be saved. The final model will be saved and will be saved for classification. The age classification system. It was distributed into 9 different categories: 0 to 6, 0 to 12, 7 to 12, 13 to 17, 18 to 24, young adult, 25 to 34, early middle age, then 35 to 44, 45 to 54, 55 to 64, and 65 plus. Then the model used a sub-layer A softmax layer generates a probability distribution across all the defined age groups, and the highest probability was selected as the best as the prediction. Then this is the optimization progress across the 5 generations, and the best was at the fifth generation. Then the best fitness of 0.1672 with a learning rate of 0.0011. The drop rate of 0.28 on closing layers of 4, then the best batch size of 16 was chosen, and the fitness curve was shown in figure 3.3. The first 3 generations was just at 0.1604 and later moved to 0.1614 before it moved to 0.1672. And these are the results. An accuracy of 94.4% was achieved with the optimized with the parameters, the optimized hyperparameters. A precision of 95%, a core of 94, F1 score of 94 on a total of 270 images. Then the table shows the performance across the categories. It was observed that 0.6 had a perfect age 0.6, 18 to 24, 35 to 44 had a perfect accuracy of 30, then followed by 13 to 17, 29, then 25 to 34 and 55 to 64 had an accuracy of 28, then the require a correct classification of 28, an accuracy of 93.3 as stated in the table. Then this is the result, the graphical representation of the result. We saw that the model achieved a perfect accuracy, 100% in the age of 0 to 6, 13 to 24, and 35 to 44 ages. Even in challenging categories like 45 to 54 and 55 to 64, which typically exhibit overlapping features, the model attained an F1 score of 0.95 and 0.92 respectively for the two age groups. And the uniformity of high scores across all metrics, it confirms the model's robustness, generalizable capability, and enhanced sensitivity to non-linear and fine-grained facial aging patterns. When the performance was compared with the baseline CNN model, it was observed that the accuracy was very low, almost times 2 of what we have in the DARA, 0.44, precision of 0.47, recall of 0.44, and the F1 score 0.43 on the same data set, while the optimized one gave an accuracy of 0.94. Then the fairness evaluation, demographic parity. It was evaluated according to these three: demographic parity, equalized odds, and disparate impact. So the demographic parity shows that the uniform sample size and even distribution of prediction rates. The equalized odds shows that the recall across all the age groups range from 0.83 to 1.00, which is still good. Then the disparate impact shows that the predictive accuracies falls within the acceptable fairness range of the 80% rule. In conclusion, the differential evolution with reinforcement learning algorithm enables fine-tuning of sensitive hyperparameters based on performance feedback, providing more stable convergence patterns and allowing the model to generalize effectively across diverse facial images, especially the black images that was experimented with. And the key contributions include integration of DA and RN for dynamic hyperparameter optimization, improved classification accuracy for black facial features, and enhanced fairness across all age groups. And finally, we reduce mean absolute error of 1.016 label units. These are the selected references. Thank you for listening. Hello. Yeah. Hello.
Yes, hello,
Yeah.
Misa, Anissa. Hello.
Do we have any questions? Auditor?
Yeah, I have a question. Your data is about 900 something. Is
Yes.
Yeah, okay. So I saw just now your data is variety from the age. Uh, mean you classify based on the age. Is it any others classify based on the zone area, domicile, uh, and others maybe?
Yeah,
Oh,
I don't understand, sir.
sorry.
I said you should repeat yourself.
Oh, yeah. The classify your data. Just
Yes,
now you slide classified based on age. Is
yes.
there any others
Nine.
classify
Any other work on classification based on the age group?
the age group by zone area, the domicile, zoning, uh, others classify? Is it any other?
No, I just classified age group and
Only age
the
group.
group age group. Yes, and it's 9 age groups from infants to adults.
Oh,
Age group 0 to 6, 7 to 14, 15 to 17, 18 to 24, up to 65 plus. It's an age group classification task, but it's just for black faces because we
okay.
have little classification for black faces just to ensure fairness.
Okay. Okay. Yeah, yeah. Only by based on the age. I mean the sex. Don't consider the sex, male or female, zoning
No,
area.
I considered both sexes, male and female.
Okay,
I
okay.
considered both male and female.
All right. Thank you. Yeah.
All right, thank you.
May I ask a question?
Okay, sir.
Engineer Matthias, it's Mohammed Altaf Hussain. Thank you very much for the insightful presentation that you have given us. And just one question that I think I must ask. Um, how do you measure the fairness and accuracy in your model across various demographic groups?
Yeah, I use just a demographic group, which is black faces. So I measure the fairness across age group, not across demographic groups. It's across age group, not across demography, because they are just black faces. All the images I used were black faces. So the fairness was measured across age group.
Okay, thank you.
All right, thank you, sir.
Thank you so much for the presentation. Now we'll be moving on to the next presenter. Next up, we have Pushpajit Srivastav with the paper title Cloud Immune System, an AI-based security framework for cloud environments inspired by biology.
So yeah, thank you everyone for joining. So our paper is on cloud immune system, is an AI-based security framework which is inspired by biology, and it's a bio-inspired adaptive and intelligent cybersecurity framework that mimics the biological immune response or human body's response to pathogens. And we tried to mimic it using AI and cloud native technologies to autonomously detect the anomalies and learn from the threats and respond dynamically to evolving threats. So cloud computing has revolutionized the every field. I mean, there's no area untouched. I mean, earlier we used to say the cloud is the thing of the future, but now I think it's think of the present. Like all the small businesses, large businesses, medium-sized businesses are using it. So and with this increment, the threat vectors are also increasing. So an innovative defense mechanism is needed, and that goes beyond the normal conventional security system, which are currently like rule-based systems, and that goes beyond that. And so that's why this paper draws inspiration from the human immune system, and represents the concept of cloud immune system, a bio inspired adaptive and intelligent cybersecurity framework where large language models, for example, Amazon's SageMaker, Guard Duty, and custom models can be utilized as ML models, and can be utilized as a brain of that particular system, which can be used in learning and getting better and better over time. So this cloud immune system autonomously detects the anomalies, learns from the threats, responds dynamically to the evolving threats. And this paper outlines the theoretical foundation of this system, and they highlights the major parts and components. And there are like few demos I believe there were like 4 demos that we created in real time, and uh, provided provide the representation how it can be done. So a little bit background, like the exponential growth about the let me go to the next slide. The cloud computing growth, I mean, this has transformed how organization operating these days, offering scalability, flexibility, cost efficiency. However, I mean, it comes with a price of increased complexity and new cyber threats. And traditional cybersecurity models or methods are typically use-based, reactive, and perimeter focused. So they struggle to cope up with the zero-day vulnerabilities, and polymorphic malwares, and advanced persistent threats, so on and so forth. So what the limitations of current system is, yeah, I mean, they are not that intelligent, and they are centralized. So we try to create a framework which is more intelligent, decentralized, and has adaptive systems that can learn from the past attacks, detect anomalies in real time, and initiate the automated response. So in biological systems, uh, there is an effective mechanism to detect, learn from, and neutralize threats. It operates autonomously, adapts to new pathogens, and maintain memory of faster future response, called, for example, it's called cell memory or like muscle memory. These characteristics have inspired a new paradigm in cybersecurity, which is bio-inspired security AI, which mimics this human body. So what human immune system has is a complex, decentralized, adaptive network of cells, tissues, molecules, uh, uh, that defends the body against the pathogens. And there it has like 2 main components. One is like innate immunity, which is like first line of defense, that offers non-specific response to invaders like your skin, or like inflammation in your body, and immune cells like macrophages that recognizes the general threat patterns. So these are the very basics one, and that are first line of defense. Then comes the adaptive immunity, that is a specialized learned response that involves lymphocytes, leukocytes, B and T cells that target specific pathogens. And it includes memory cells that enable faster response upon re-exposure. So key characteristics of adaptive in immunity is self versus non-self recognition, pattern recognition, immunological memory, distributed and redundant operations, and signal amplification and cascading response. So here what we did is we tried to draw parallels between biological immune function and artificial intelligent mechanisms in a cloud environment. So for example, innate immune system is something that detects and responds quickly to general threats. And on cloud environment, these can be similar to signature based anomaly detection. And then adaptive immunity that learns and improves over time, can be similar to machine learning models trained on evolving threat data, such as SageMaker, GuardDuty in Amazon. But yeah, of course, on the other cloud environments, they have the similar counterparts. Then PRRs, they are similar to behavioral analytics and threat intelligence feeds that identify the known molecular patterns. Memory cells are something that retain the history of previous attacks on the body. So similar in the cloud environment, we have threat databases and models retaining with the model retraining with this historical data. Then comes the cytokinase and signaling, which coordinates the defense actions. This is event driven and can be done by functions like Lambda or custom code according to a need, and sending notifications to users using services like SNS. By leveraging this analogy, CIS can be designed as a distributed learning-based security system capable of defending the cloud infrastructure proactively, and improves over time. Then there are like few major components of this framework. The first one is data collection layer, which can be the first line of defense. That can be your skin, immune cells in human body. Similar in the cloud environment, we have AWS CloudTrail that tracks the API calls and the user activities. Then VPC flow logs that monitors the network traffic. Then another example could be CloudWatch logs and metrics that gathers the system's telemetry, and the GuardDuty findings that aggregate the threat intelligence. On the detection engine side, it is similar to pattern recognition receptors. And on the cloud environment, it can be these duties can be fulfilled by Amazon SageMaker that trains and deploys the anomaly detection models. GuardDuty does the same when it comes to firewall or security related issues. Then Amazon Detective is one of the product that visualizes and that investigates the attack paths, and custom auto encoder models for the behavioral anomaly detection. Third part is decision making and memory engine that is in human body that are similar to lymphocytes and leukocytes that recognizes the specific threats and that adapt over time. So in the cloud environment, we have DynamoDB that stores and learns threat signals or threat signatures and responses. Then SageMaker pipelines that update the ML models with new threat data. Kinesis firehose that ingest the real-time log streams for learning and event bridge route signal based on rules and behaviors. And the last but not least, the response engine, of course. So like human body has antibodies and killer cells eliminating the infected area. On the cloud in the cloud infrastructure side, it can be a function that initiates automated remediation actions. It could be SSMs that isolates or patches the compromised system, and a step function that orchestrates multi-step functions, and the notification system such as SNS that sends alerts to stakeholders. Well, there was and this all architecture, or the parts of the architectures, they perform in loop. That's why when the feedback loop comes into picture, memory cells ensures the faster response to the threats next time. Examples could be S3, Athena, SageMaker, and so on and so forth. Here is the flow log, system flow log, and decision-making logic behind this framework. First one is sensing. So data is collected from the AWS resources that collects logs, and could be audit logs, could be network logs, could be systems log itself. And example of this could be CloudTrail, Flow, guard duty logs. Then comes the deduction part, that where the LLM or SLM models and detects the anomalies and unknown behaviors. After that, the classification part comes into the picture, where they classify those alerts or events as a benign or malicious using a scoring model. And on the basis of that, they respond, I mean, whether to isolate that particular system, or like to patch it or disable it. That based on your function, lambda function, or like any other Python code or any other code that you have created. And the last part is the learning, that system logs these activities and feeds these outcomes back to the training data set. Here I have added one example, one use case. I mean, on the paper we have submitted 3 use cases. And yeah, on the GitHub we have provided a repository where we have multiple use cases and the code and everything, like the step-by-step guide to perform it. So this one is an example of an insider threat modeling, where where the uh, internal user tries to compromise the system, and a malicious actor basically try to use an EC2 instance, initiates an unauthorized data exfiltration. So in order to isolate this threat, CIS takes into effect, and the response is yeah, comes from the same flow that we discussed in the past slide. Like first layer would be the detection, and could be your Amazon VPC flow logs that reveal abnormal outbound traffic. And a SageMaker machine learning model identifies this behavior based on its training as anomalous. Then comes the containment stage, where event bridge rule is triggered, and activating the lambda function to automatically isolate this compromised EC2 instance by modifying security groups and network access control lists. Then comes the notification parts, where the simple notification services sends an intermediate alert to a security operations team. And the last part is the learning, where the incident is logged and details are fed into the future model training pipelines, and to enhance the detection and to increase the efficiency of the similar to memory cells. So that when the next time this similar attack happens, it recognizes it and try to and resolve it in with ultra low latency. Then strengths of these models are adaptive learning that mirrors human immune system capabilities with continuous learning loop, powered by SageMaker and other ML models. Then automated response which is basically low latency automated response to incidents, reducing MTTR. Then this framework is cloud native and scalable. I mean, we have started developing it through AWS, because I had some experience from AWS side of the house, but there is still scope that where we can utilize other cloud providers and develop something similar on that as well. Challenges, false positive, like when we were performing the doing the labs. So during the initials, or like during initial stages of training, or during initial stages, sometimes misclassifications, especially uh, when you begin training the model, can sometimes lead to false positives. Model drift. Model requires a frequent retraining to avoid concept drift as normal changes over time. And complex integration, since we are using using multiple AWS services at the same time, it requires its expertise, skills, or experience. So this is something could be the challenges. Future research directions could be federated learning for cross-training, cross-thread sharing that enables CIS system across the organization to share the anonymized thread data without exposure to the raw logs. Another one could be multi-cloud and edge integration. So yeah, since we started with AWS, but there's a scope where we can utilize it with other cloud providers like Azure and Google Cloud. Then neuroimmune inspired architectures is also something that can be utilized with this CIS. So that can provide dual layer defense, which can be more effective, because yeah, of course, because there we one is better, like two is better than one. Then open source CIS framework that can be used to develop and publish an open source reference implementation using AWS SDK or Terraform, which is code as a service or infrastructure as a code. And the cloud immune system sets foundations for self defending cloud ecosystem that will continue to evolve alongside with emerging threats. So this is the end of my presentation. If you have any questions.
Yes. Have you test as alive for the immune
Yes.
system? Yeah.
Yes, we in the papers, in this particular paper, we have like three scenarios. The one that I presented, there are two more. That was like ransomware and malware, and other one was API breach. So these are the three ones. Actually, there were five, because could only accommodate three because it was increasing the size of paper. So I included three in that. But on the GitHub, I'm gonna provide all the results of all five scenarios that we have tested.
Oh, okay. How is the performance? Is it
Yeah, performance wise, I mean, the when we were doing the literature review, there was one immune system AES that was developed for network side. It was detecting the suspicious packets like within 3 seconds. The one that we have developed, the longest it's taking is 3 milliseconds. So I would say it's like quite effective. It's significant improvement. I would say 10 times improvement when it comes to ultra low latency.
okay? Okay, thank you.
Thank you.
Srivastav, I have a few questions, if you may answer.
Sure. I'll try to.
Okay. Well, you have mentioned during the course of your presentation that there have been false positives and the misclassification, so the model needs to be retrained. So that is like a mod collapse in networks. So have you quantified this? That what's the frequency of your network to collapse and how to mitigate those things?
Yes. So when we started it, the rate of those false positive was around 5%. And it was minimal. And the thing is, these models, because I didn't created the model by myself. I was using Amazon SageMaker, and for firewall side of the house, we were using Guard Duty. So they have their own large language model, because at that point of time they were utilizing 4.0, GPT's 4.0, I believe. Now they move to 5.2. So I believe this will significantly reduce the false positives and the isolation. So the reactive action would be more accurate.
Just another minor question. Um, since I also do research in networks and machine learning, uh, there is a pressing issue in machine learning algorithms. It's the catastrophic forgetting of the networks. I mean, you train your model on a certain data set, but once you use that trained model on any of the other data sets, so it does not give you the best results. So do you feel that the model you're working on, it would be able to reproduce the results, or it may uh, implement the generalizability, which is much stressed nowadays in research?
Mm, I would say, I mean, can you please repeat your question? I'm trying to
Okay.
find the answer. I'm trying to think the answer, but I want to make sure
Okay.
I correctly.
Sure, I'll repeat for your consumption. But there is a pressing issue in the networks that you train your model. So it gives you suitable results as you intend on a particular data set or for a particular task. But once you apply that trained model on any of the other data set, may it be similar to the other one. So there is a term known as the catastrophic forgetting in machine learning models. So do you feel that the model you're working on, and of course you must have trained it well, so do you think that when it will be applied to any of the other data sets, so it will be able to replicate the results or the accuracy? I'm asking this because nowadays there is a lot of stress on research regarding the generalizability or the
Right, right.
reproducibility. So that's my question.
I would say it should be able to, because so when we tried different data sets in our utilizing this framework, like first we use the standard ones that is available online through, and like the CISSP packets, or the standard packets that we can download from the internet. Those ones were working fine. Then we initiated custom use cases that we developed our own, like not utilizing those packets, but since we trained the model on that one, and now when we were doing it like doing manually, like somebody is using Tor browser and going utilizing the VPN from the Germany, from by training the old data sets with these standard ones, and then doing this manual trial. I mean, it recognized it. I mean, for some reason, I mean, not for some reason. I mean, of course, since we trained
Okay.
it, it
Yes.
recognized that the user is coming from Germany, not from the US. So it isolated it, but same time it didn't block the access of user. So it just gave the user read only access on certain resources, but the same time it sent the SNS notifications to the responsible stakeholders. So I would say yes, it worked. So yeah, I mean, I think is future of this one with more training and training. I think yeah, at the end of the day, it should be able to resolve that kind of scenarios as well, where uh, there is a set of like standard sets, and there is something else that's not defined under the standard set of data.
Thank you, Srivastava, for the insightful presentation and answers to my questions. Thank you very much.
Thanks.
Thank you so much for the presentation.
Thank you.
Now we'll be moving forward to the next presenter, and we have Fatima M. Rahim with the paper titled Efficient ECG Signal Classification Using Kalman Filtering, Attention-Based CNN, and Knowledge Distillation.
Good afternoon, respected comments. It is my honor to present our paper titled Efficiency ECG Signal Attention Besides CNS and Knowledge Distillation This presentation highlights a novel approach to ECG signal classification that integrates Kalman filtering for denoising, attention besides CNS for future extraction, and knowledge distillation for efficient model compression. Our objective to facilitate real-time arrhythmia detection on a lower resource device, enhancing this stability and effective on cardiac monitoring. 79 million deaths for CVDs annually. Cardiovascular account for an alarming 79 million deaths annually worldwide, highlighting the urgent need for effective monitoring solution. The ECG, the gold standard of diagnosis. The ECG are recognized as the gold standard in diagnosis heart condition, providing vital insight on heart health. A growing demand for wearable monitoring. The rise of wearable devices has led to an increasing demand for continuous ECG monitoring, enabling protective health management. A challenge in ECG. The key challenge include noisy ECG signal caused by patient movement, muscles activity, and electrolyte shift in nucleoside class imbalance and limited resource in portable device. Research objective. Our objective is to create an ECG classification framework that is precious, efficient, and lightweight, enabling real-time processing on embedded device. This balance ensures that the model is suitable not only for hospital environment, but also for portable device, facilitate continuous health monitoring for user. A signal enhancement with an HKV. The first stage signal enhancement implies as hierarchical Kalman filter for effective abductive noise removal, ensuring cleaner ECG signal for analysis. Deep future learning via CNN. In the second stage, deep future is containing through an attention besides CNN, which acts as the teacher model, capturing critical ECG feature for improved classification. Mold compression through knowledge distillation. The final stage involves model compression through a knowledge distillation, creating a smaller student model that maintains performance while being suitable for development on lower resource device. Dynamic Kalman filtering. In the first stage of the framework, a dynamic Kalman filter is utilized to process segment of the ECG data, especially 118 sample heartbeat segment. These segmented are detected using R peaks, enabling devices focus on each heartbeat. The filter effectively removes both board bind and baseline noise, enhancing the clarity of the ECG signal. Signal smoothing. The second stage as a standard Kalman filter to smooth over the entire ECG recording. This stable provide an overall smoothing effect, contributing to improve signal quality across the full duration of the ECG data, while perceiving critical waveform characteristics. Improve signal-to-noise ratio. The application of the Kalman filter results in significant improvement in the signal-to-noise ratio, typically enhanced to 6 to 10 decibel. This improvement is critical or important for maintaining the integrity of the ECG waveforms, which are essential for accurate diagnosis and monitoring of a heart condition. High capacity CNN architecture. The teacher model is designed to handle 118 sample ECG windows effectively. It compares several layers such as Convia 1D for confusion operation, max spoiling for downsampling, and dropped for regularization. These layers are recognized into 3 blocks with 64, 1 to 8, and 2 5 to 6 filter, respectively, enhancing the model ability to learn complex patterns. The model is also include global average boiling to reduce dimensionality, followed by a Denise layer with 5 to 1 2 units, plummeting in the output softmax layer. The structure allowed the model to achieve an impressive accuracy of 99.96 presented on the MIT PIH dataset. Limitation of a simpler model. In contrast, while a simpler models may utilize fewer layers or lack attention mechanism, they often fall short in accuracy and feature extraction capacity, such as models might not capture the suitable ECG features necessary for distinguish between closely related heartbeat type. The feature models high capacity RT architecture enhanced with attention mechanism enables to outperform simple models, making it partially effective for tasks requiring precise classification of ECG signals. Knowledge distillation enhance model efficiency. Knowledge distillation is a technique that enables to the transfer of knowledge from a large, more complex teacher model to smaller student model. This process relies on soft interoperability outputs from the teacher to guide the learning of the student. The student model is streamlined, consisting of only two comfy 1D layers, global average boiling, and the softmax layer, achieving an impressive accuracy of 97% deceived in the smaller size. It demonstrates remarkable speed and efficiency by making the decision-making a process of the teacher, the student, not just the outcomes, but the underlying reasoning, improving its performance in real-time application, data set, and the pre-processing. MIT B1H arrhythmia database. The MIT PIH arrhythmia database consists of 48 two-channel ECG recording, providing a rich source of analyzing heart condition with a standard sampling rate of 16 Hz, facilitated dilated waveform analysis, class imbalance management. To address class imbalance in the data set, techniques such as scientific minority oversampling feature and random undersampling were implemented, ensuring a more equitable presentation of normal and abnormal beats. This segmentation was performed dividing the ECG recording into 190 sample windows, which help in consistent analysis and improve model training efficiency. Benchmark dataset. This dataset is a widely recognized benchmark for ECG logarithms, enabling research to evaluate their model against established standard. Special attention was given to maintain balance, preventing the toward normal peace during model training. Results. Overall accuracy. Achieved 97% overall accuracy for classifying 5 different arrhythmia classes as per the AAMI EC 57 standard. High precision and recall. The precision and recall rate exceed 95 for all arrhythmia classes, indicating strong motor performance across categories. Confusion matrix analysis. The confusion matrix indicate high diamonds, suggesting effective classification with minimal misclassification. Effective beat definition. The model effective definition between visually similar beats such as class A and class N while maintaining accuracy. Result training behavior. Training lasted 2015 epoch. Training loss research 0.1, and validation accuracy is stable at 97.12. No overrating detecting. Regularization technique applied. Thank you for listening to our presentation.
So you're welcome.
Hello.
Yeah. Normally the equipment, in this case, use ECG to classify using Kalman filtering. So normally when we install the equipment, there is some noise.
Excuse me, I can't hear you.
Sorry. Hello, can you hear you?
Hello.
Yeah. Okay. Can you hear me? Hello?
Hello. Yes, I can
Yeah,
hear
okay.
you.
Okay. Normally when we install the equipment, in this case is ECG, there is some noise like the placement, the transferring data, the communication, some noise data. So how about this some noise data, the reading or something? Is this in this filtering? The Kalman also can do this something noise data or something like this.
Excuse me, sir. Can you ask in the chat? I don't hear you. Hello.
Okay, yeah.
Yes, there's some audio issue. Got it.
Normally, when we use equipment, this case is ECG. When we measurement, when we install the ECG to the body, there is some like noise data, communication sometime interrupt. So is how about this noise data, the reading problem? Sometime the patient just now you saw how the patient use wearing the ECG equipment. Sometimes they are moving. Accuracy of the data is not matched to the reading. How about this error or noise data?
First segmentation. First segmentation signal on the filter Kalman, and the second segmentation السيجنال على الفلتر كمان
I cannot hear you. It's okay.
Can
Okay.
you ask in the chat? Okay.
Okay, so we'll be moving forward to the next presentation now. And next up, we have David C. Bonilla with the paper titled Gemini's Observability Module Monitoring the Environmental Sustainability of IoT Infrastructure.
Okay, now it's working. Okay, so for the introduction, we have a few problems. The first one is that the data networks consume an estimated 260 to 360 terawatts per hour in 2022, emphasizing the urgent need for sustainability in IoT infrastructure. The IoT systems, while enabling advancements in smart cities, healthcare, and automation, pose significant environmental sustainability challenges. The traditional ICT sustainability metrics focus primarily on energy use, but overlook factors like e-waste and resource utilization. And the rapid growth and short life cycles of IoT devices exacerbate electronic waste challenges, requiring more comprehensive evaluation methodologies. These different factors we found through a literature review that I did for my PhD studies. And the main thing that we found is that almost all the sustainability initiatives are all related basically to electrical consumption. That's why we introduced Gemini's, that is a green evaluation methodology for IoT and network infrastructure sustainability that integrates diverse sustainability metrics to provide an holistic assessment of the environmental impact of the IoT infrastructures. Our methodology is based in a cycle that it's composed by three different stages: the observability stage, the analysis stage, and the control stage. For this specific paper, we are going to focus in the observability stage, in which we define the environmental sustainability metrics that we are going to use for reviewing the IoT systems, the deploying of the monitoring tools, the data collection infrastructure, and also we are going to see a little bit of the data integration and processing and the sustainability performance metrics. Okay, so this is the ITU IoT reference model. Here we have the 4 layers: device layer, network layer, service and application support layer, and application layer. And we have the defined metrics that we propose. Those are power usage effectiveness, water consumption per infrastructure, electronic disposal efficiency, electronic waste, greenhouse gas emissions, network electronic consumption, and the ICT capacity and utilization. Through the architecture of the IoT ecosystem, we decided that the PUE was going to be measured in all the different layers because it's all related to infrastructure. The water consumption for infrastructure is going to be measured in the device layer, network layer, and service and application support layer. Electronic disposal efficiency and electronic waste, it's also going to be measured in the 3 first layers. The greenhouse gas emissions and the network energy consumption is going to be measured in the device layer and in the network layer. And finally, the ICT capacity and utilization is going to be measured in the 3 layers: device, network, and service and application support layer. This is made so we can guarantee that we are doing a full view of the IoT scope and that we are not missing relevant information from any of the layers. So talking about the metrics, what we did was define a mathematical model that allow us to measure these metrics and to organize them to calculate a final sustainability index. So for the water consumption per infrastructure, we had 2 different phases. The first one is the operation phase of the IoT deployment. Those are the water consumption infrastructure for heating, ventilation, and air conditioning, and the liquid refrigeration for those devices that requires. For example, if you have a private cloud or you have an AI running for processing your data, you may have super servers that require liquid refrigeration. And the second phase of the WCI is the production phase of the devices that you use in the IoT deployments. So we try to also bring the inferred water that we use to actually produce the device. So we have the water for extraction and the water for fabrication. So basically, the full indicator is going to be the sum of all the water used in the production and in the operation measured in liters by hours. Then we do a normalization of this value. This is because we need a value between 0 to 1, in which 0 is less sustainable and 1 is the more sustainable that you can get with this indicator. So the proposed metric is for the WCI normalized is 1 minus the measured WCI, that it's going to be this value, over the WCA maximum. And this is a value that you can get when you make observations on the infrastructure and its components. Then we have the network energy consumption. This is the energy that all the network components consume. So here we have the sum of all the routers energy, all the switches energy, all the access points energy, all the base stations energy, and all the IoT devices energy. So we have a full scope of the network ecosystem of the deployment, and the normalization is the same formula as for the WCI. Here, the maximum network energy consumption is going to be a reference value based on the observation of the structure and its components at the maximum operation and capacity of the system or the deployment. Then we have the greenhouse gas emissions. For this, it is important to realize that there is a emission factor, and the emission factor varies by country. So the emission factor here in Colombia is different than the emission factor that we have in Canada, and that's different than the emission factor that you have in England. This metric is measured in grams of CO2 equivalent using the emission factor, and the formula is going to be basically the network energy consumption times that emission factor. We are only calculating the greenhouse gas emissions of the network infrastructure. For the normalization, we use the same formula as that we use for water consumption, energy, and network energy consumption. And here, the GHG max is going to be the network energy consumption maximum times that emission factor. Then we have the ICT capacity and utilization. This evaluates the resource and communication links utilizations relative to its maximum capacity. So this is basically a percentage that we have between the used bandwidth and the total bandwidth of the IoT deployment. And for the system is the used system capacity over the total system capacity. Here we are talking about megabits, kilobits, gigabits, depending on the bandwidth of the system. And here we are talking about the percentage of the processing capabilities and usage and storage usage of the total system. For the normalization of this metric, this was the most trickier one. We decided to use a Gaussian function with the standard deviation at 0.17 and the mean at 0.6. This is to penalize under and overutilization, looking for optimal values of between 40% and 80%. Once that we apply this Gaussian formula, what it does is that allow us to have the distribution in a normal distribution. And when we apply the normalization, we can use the function over the maximum of the function that it's going to be when it's 60%. For the electronic waste, it measures the waste generated by the device through its entire life cycle. This is measured in kilograms per year. And the formula is basically the weight over the lifespan. So for example, if we have here a device that it weighs 200 grams and its lifespan is 10 years, then we are going to have 20 grams per year as the measure of the electronic waste. And normalization is the same formula that we have in the first metrics. And the EW max depends on the evaluated device. This is because depending on the configuration, you can have a longer lifespan or a shorter lifespan. For the electronic disposal efficiency, it represents the proportion of the discarded devices that are properly recycled. So the definition of this metric is the percentage of recycled devices over the total discarded devices. This is already a ratio between 0 to 1, so there is no need to normalization. That's why EDE is equal to EDE prime. And finally, we have the power usage effectiveness. So adapted to IoT, this is a metric that is well known and widely used in, for example, data centers. So adapted to IoT is the ratio of the energy used by all the computing devices related to infrastructure, that it's called TCE, total computing energy, to the network energy consumption. So what we want to measure here is how much energy we are using for the network infrastructure compared to the complete infrastructure related to the IoT development. This could mean, for example, the final device users, the different screens where we show the information of the devices, the energy that we can use in the private cloud or in the actual cloud, if we can measure that with some different techniques. Once that we have that radio, we do the normalization. That would be the inverse number. So we can have a value between 0 to 1. So finally, we have the Global Sustainability Index.
Actually, you have completed the allotted time slot, so if you can please conclude the presentation.
Sorry, can you repeat that?
Yes, okay, you have completed the allotted time limit, so could you please conclude the presentation?
Okay, just give me 1 minute to finish. We have the Global Sustainability Index in which we measure the complete system so we can evaluate it. And this is going to give us a value between 0 to 1 to show us how our organization is sustainable or not. Then we did a model validation using different sensors that we have in our campus in Los Andes University in Colombia. After we applied the model, we can observe in the case one that using normalized weights of 0.2, we have a value of 0.5 as the global sustainability index. In a different case with different weights, the value can change. So the weights are adaptable for different sustainability goals of the organizations. And I guess that for the discussion and conclusions, you will have to read that on the paper so we can have time for the questions. I'm so sorry for taking long.
Yes, thank you, David, for the presentation. Have you measured the all the parameter that you mentioned just now?
For the validation of our model, we measured 5 out of 7.
5 sets of the data.
Yeah, 5 metrics out of the 7 that we have. Just give me 1 second here. So for the deployment, we measured the water consumption for infrastructure, the network energy consumption, the greenhouse gas emissions, and the capacity and utilization of the system. This is because for the specifics of the deployment that we decide to use, it was a lot dedicated connection. So we actually didn't measure the capacity of the network because the link was dedicated to the communication. The electronic disposal efficiency was not measured because there is no data for that specific deployment of how many devices have been used and have been discarded. And as it was a dedicated connection between just the sensors and the base station, there was actually no more computing infrastructure that we can use to measure the PV. So these 3 metrics are the limitations in the scope of our model validation.
Okay. This data based on the measurement on the field, is it?
Yeah, it's on field in a real deployment that we have in the campus infrastructure of Universidad de los Andes.
Okay. All right. Thank you.
Thanks to you for the question.
Thank you for the presentation.
Okay, thanks.
Moving forward to the next presenter of the session, we have Muhammad Altaf Hussain with the paper titled SAE Swing Sparsity Aware Efficient Swing Transformer for Virtual Histopathological Staining. So Muhammad, if you're present in the session, you can start with your presentation now.
Thank you very much for the opportunity, Disha. I hope the screen is visible so that I may start.
Yes, it is. Yeah.
Okay, thank you very much. Thank you very much for giving me the opportunity to present my paper, which is the sparsity aware efficient swing transformer for visual histopathological staining. The authors who contributed with me, their names are as flashed. Before we proceed, I would just like to introduce myself. My name is Mohammad Altaf Hussain. I am from Pakistan. I did my bachelor's in mechatronics engineering from National University of Sciences and Technology, Pakistan, and did my master's again in mechatronics from the same university. Currently, I am a PhD scholar in the biomedical engineering at the same institution. My research interest includes image processing, GANs, vision transformers, neural networks, like that. The sequence that I shall be following for my presentation is as flashed. The histopathology involves examination of tissue samples under a microscope, the extraction of tissue sections for examination. This process is known as the biopsy. It is an invasive process, and in the last 2 decades or so, the number of biopsies they have increased by 140%. Biopsy samples can be taken by various methods, as they are already shown in the figures as well. There have been the 5 methods, as you can see. Since the extracted tissues, they lack features which are needed for the diagnosis, so we dye the tissues with certain chemicals to highlight various tissue sections or their cellular structure. This process of dyeing those tissues with the chemicals is known as the staining process. The staining adds color and contrast to the tissue, making it easier to see pathological features. Amongst the different stains, hematoxylin and eosin, commonly known as HNE, is the most common stain because it covers 80% of the staining performed globally. HNE is a combination of stain where hematoxylin gives purple color to the nuclei, and eosin dyes cell cytoplasm with pinkish red color. But there have been certain problems with the traditional staining. Stains can be affected by inconsistency during the tissue preparation. Different labs, they have different staining styles. HNE staining is normally cheap, but staining with other chemicals, it is expensive. So depending upon the type of the stains used, staining process can take from somewhere 2 hours to 24 hours and even more in few cases. Staining and its pre-processing steps can deform tissue samples because staining is destructive in nature. And at the same time, the chemicals being used for staining like formalin, ethanol, hematoxylin, they are harmful, toxic, and cancerous. So we need to overcome majority of these issues by digital or virtual staining. In virtual staining, we use deep learning based models for staining tissues. This is a non-invasive process, so it provides a suitable alternative. At the same time, it also minimizes the use of the hazardous chemicals, as already said. And this can make the histopathology safer and even more efficient. But there are certain challenges with the virtual staining process. The virtual staining process using the convolutional neural networks and the GANs, they have their limitations because they have difficulty with the global context due to localized receptive fields. This limitation may lead to the introduction of artifacts in the fine-grained textures and inadequate modeling of the subtle morphological features. Vision transformers, they provide an alternative in this case by modeling images as a sequence of patches known as tokens. And they also apply self-attention to capture global context, which CNN organs can't. But vision transformers, they have their own limitations, which is the computational cost and over-smoothing of the images during the inference stage. So this inefficiency is a major obstacle for deploying vision transformers for processing the high-resolution images. To improve computational efficiency and other issues that have highlighted, the researchers, they have developed various hierarchical transformer models like swim transformer. The swim transformer builds upon the multi-scale features for improved computational efficiency, local attention, so that the complexity of the computation is reduced. And also it strives to strike a balance between the local and global attention effectively. but it also suffers from redundant computations as well. And at the same time, it is prone to smoking because of the dense computation. So there is a proposed solution for this, and for that we have introduced SA swing in our paper. That is a sparsity-aware efficient swing transformer that reduces computational redundancy and mitigates the oversmoking. And we have achieved this by introducing three core modules into it. The first one is the sparsity attention mechanism. Its details will be covered in the later part of the presentation. The second one is the adaptive feature recalibration. The third one is the hierarchical residual refinement. So by integrating these three modules into the baseline swing transformer, we have been able to reduce the inference latency and the memory uses. And at the same time, we have achieved a superior sustained fidelity and perception as well. The proposed methodology of our method first includes the introduction of the dataset. We have used the e-staining derma repo dataset, which is a dataset of skin histology. This dataset has been made publicly available. This dataset contains 87 whole slide images of the various skin conditions. So since the whole slide images, they are of gigapixel scale, so we cannot process them normally. So for that purpose, you need to convert those images and you have to reduce their size. So for that purpose, we have divided the images into 512 by 512 pixels. And also we introduced overlapping between the consecutive patches. We excluded the plain background patches using the adaptive thresholding when the data augmentation was used to prevent overfitting and improve generalization. We also did image registration to avoid the pixel misalignment. And then to mitigate the issues of scale and the feature transform invariance, we introduced random flips, rotations. So as you can see from the figure, this is a raw unstained slide and how the tissue is separated. Then performing all these steps which I have mentioned, you achieve the required image. So our proposed model, the SA swing builds on the standard swing transformer architecture. As I've already mentioned, it targets three core modules. The first one is the sparse attention mechanism. And in sparse attention mechanism, instead of considering every token interaction, we dynamically prune attention to focus on the most informative region so that we reduce the redundancy. And this is achieved by applying a binary mask, as you can see in this equation. This binary mask places a threshold value that small values below a certain threshold, they are set to 0 to reduce the computation. And this approach cuts down on the attention size, the floating point operations, and memory usage, similar to a recognized technique known as the adaptive token sampling. Then our second innovation in this module is the adaptive feature recalibration. And this focus on important tissue structures or stains by emphasizing certain channels and suppressing others. As you can see from
Dear author, we'd like to remind you of the time limit.
Sorry?
We'd like you to remind you of the time limit. We have crossed the 10 minutes. Yeah.
Okay. Thank you. This module that utilizes the global average pooling and converts them feature maps, and it goes through the multi-layer perceptron. And the third one is that to overcome the over-smoothing, we create one-to-one configurational residual links. They preserve the high frequency details, although they also add a negligible overhead as well. So this is the architecture of the baseline swing transformer, and this is the proposed model. And we have shown here the transition of the both the models and the modules during the virtual staining process. So the last step involved is the reconstruction of those patches so that the whole image is recreated. But there's a particular concern regarding the visual inconsistency regarding the color and the contrast once the patches they are merged. So once they are merged, they introduce artifacts and they compromise the diagnostic fidelity, as you can see in the upper half of the image. So we employed cosine window blending, color normalization, and overlapping weighted averages. So in the end, the final image looks quite smooth, crisper, and very natural. We have evaluated our model on a comprehensive set of quantitative layers, and at the same time, we have also computed the computational cost. As you can see here, that our model that outperforms the baseline swing transformers in all of the matrix. At the same time, it reduces the trainable parameters, flops, latency, and the memory usage as well. With the quantitative measures, we have also carried out the qualitative evaluations that includes the visual Turing test, stain specificity, and the artifact severity. This qualitative evaluation has been done by the three board-certified dermapathologists who were given 100 images, 50 each of the virtual stains and the ground truths. So they assess the image based upon the stain specificity and the artifact severity. And the iterated agreement was assessed on the basis of the Fleiss kappa, which is the statistical mean and overall Turing test success percent. So here you can also see that our proposed model outperforms the baseline one. And at the same time, we can see that the bottom row that depicts the virtual stains generated by the our proposed model, and this one is the virtual stains generated by the baseline swing transformer. The second row, that is the ground truth, and the first row is the unstained images. So we can see that our proposed model incurs less overstaining artifacts and hallucinations. We also performed an ablation experiment just to see the contribution of the modules that we have introduced, that how they affect the performance of our system. And we tested it on the features as shown in the table. As you can see from the results, that in all the cases, at least one of the metric worsens, confirming each module's relevance and importance. For example, if we disable the sparsity attention mechanism, so we can see that the structure similarity has been reduced. Similarly, if we eliminate AFR or HRR, even then we have seen that the latency has increased. So lastly, just to see that we can balance accuracy and efficiency, so we adjusted the token threshold in the sparse attention mechanism. We tested the attention on top 50%, 30%, and the 10% of tokens as shown in the figure. This was done to add a flexibility to the user to choose desired efficiency, accuracy, balance. So, for example, if you see that at the 30% of the token attention, the image quality, which is the structure similarity, is 0.892, which is still better than the top baseline swing transformers efficiency. So after doing so, we have also carried out SWOT analysis of our system. So our strengths, they remained that the enhanced image fidelity, as I have already covered, in terms of the image fidelity and the diagnostic fidelity, at the same time reducing the computation. There has been weaknesses as well because we have utilized this on a single data set. So we've still not been sure about the oversmoothing issues if we apply on the other data sets. And we are still working on it in a future part of our research. So, but in future, we want to expand our application to multiple organs, different staining protocols, and but with more emphasis on the clinical feedback. But still, there is I hope that we tune the efficiency versus the accuracy, and the clinical adoption of the GAN generated or the vision transformer generated virtual staining methods is still questionable because it has not yet been deployed at the clinical level. So that's all from my side, and if you may have any questions or queries to respond before we conclude this part of the presentation.
Yes, thank you, Altaf, for the presentation. Yes, we have experienced sometime the image. Just now you saw some images from the samples. Sometimes the quality is not quite good. So the image quality. Do you have experience this one? The quality of the image, the samples, data.
Uh, Thank you, Mr. Kadir. It's a very pertinent question that you have highlighted.
Yeah.
As I have mentioned during the part of my presentation, that the gold slide images, they are gigapixel in size. So we cannot process them normally. So for that purpose, you have to split the images in the smaller patches or in the tile form. So once we do that, of course, the quality of the image that is compromised or that is affected. But there have been techniques which we apply so that we get as maximum as features as we can, because that is the data augmentation technique, that the color normalization or the variance equalizations or the image enhancement techniques that we have used here. But of course, the quality of the images, because these are the patches, the of the 512 by 512 sizes. So of course, there will be blurrier images. So we try to adapt to the techniques that can output as close as to the original unstained or the stained images. But this is the digital imaging is all about, that how close you can go to the actual system or the input, may it be images or anything.
Okay. Okay. Thank you. Thank you. Anissa, I think can move to the
Yes. Okay, yeah. Thank you for the presentation. We'll be moving on to the next presenter. We have Ikini Francis with the paper
Thank you, Anisha.
titled
Thank you
Smart
very much.
Learning Ecosystem, a Case Study from China. Do we have Ikini here in the session?
Oh, yes, I'm here. Can you hear me?
Yes, we can hear you. You can share your screen and start the presentation.
Okay, all right. Can you see my screen?
Yes.
Hello.
It's visible.
Okay, I would say good evening from China and good afternoon in UK time. So my name, I'm representing a group. We worked on a smart learning ecosystem, a case study of from China concerning smart education. So the content of today's presentation centers around we have introduction, brief literature review, methodology, discussion, and conclusion. And in terms of introducing background of smart education or learning ecosystem in China, so China is governed, education is centered around the global education 2030 agenda, which prices the education system in fairness, inclusivity, and quality of education. And also in that, in trying to improve their education system, they include or kind of adopted a policy called the China Educational modernization and informatization. So in trying to digitize education system in China, they also integrated their education system with technologies like 5G, AI, blockchain, big data, digital twins, and humanoid robotics, etc. So this policy came into inception in 2018, and in that, China kickstarted numerous projects. They call it a demonstration area project. So with that, with this project, they have achieved a groundbreaking, let me say, groundbreaking achievements in that. So now, this is the typical smart education classroom in China, where this kind of movement, I would say, start from their kindergarten, then to primary school and high school, the secondary school education, tertiary institution. So this is they have the motive to catch them young. So with this, the children, the future generation will be able to, they will be not only innovative when it comes to technology, but also they will call regard as technopreneurs. So inculcating technology into maybe whatever other things they are doing in businesses, in sciences and everything. So this is the idea of this policy. So with this, having said that, given the background of this China's smart education system, so let's look into the overview of it. So China digital learning ecosystem has been been formulated in two phases. The one is called Education Informatization 1.0 and also 2.0. So the timeline for the 1.0 started from 1970s to the year 2017, which was a kind of a metamorphosis from audio-visual teaching to comprehensive IT adoption. So as of that time, they use ICT tools, but the basic ICT tools. So with this 1.0 phase, they try to progress from the elementary level of ICT to advanced comprehensive IT information technology adoption or integration in the education system. So in 2010 to 2020, that is this policy worked for like both for medium and long-term plan, and with that the 1.0 achieved the 10-year development plan for education informatization. So in that, within the 2011 to 2020, they also tried to reach a milestone of Internet Plus Action Plan and also the 13th five-year plan for education informatization. So China, when each policy plan they separated it some within the term for the plan within 10 years to 13 years before they initiate a new policy for education development. So the second phase, they launched this policy, what we call the Education Modernization 2035 from 2018 to 2021. So this policy was initiated in 2018 and is still in vogue till 2025. So they are expecting by the year 2035, they would achieve enormous, a significant milestone in digitizing China's education system. So in that, with the interest, they have established nationwide education demonstration zones and also implemented enormous innovative smart education governance structures. So, and also digital resource platform and data-driven systems. So these are the achievements of this so far with this recent policy. They call it Education Modernization Policy for 2035. So this is the roadmap of this policy. Started from January 2018 to it starts improving to okay April 2018 to January 2019 to May 2019, October 2020, and February 2021. So it's still progressing. So each year or every month, maybe four months interval, 5 months interval each year, there is a kind of a reformulation or reformation in the policy. So there is assessment and also tracking the progress and the impact of this policy in the education system in China. So with that, our study tries to use the way researchers tries to use this study, this achievement to inform other countries that are still struggling to digitize the education system, using China as a model. So the aim is to use China as a model to other countries that are struggling and also highlight the impact of China Education Modernization 2035 policy. So these aims and objectives are guided by three research questions, which is how does China modernization shape the education landscape? So that's it. Now in our literature review section, so we just want to use this diagram to buttress what a smart education system is all about. So on the left side, the diagram tries to explain that smart education or smart classroom entails a teacher and a learner making use of what technology is an intersection of what technology, learner, and teacher. So this is the basic understanding of what smart education is all about. So the technology, it determines what kind of technology do we have in our school system. So on the right side, this is just a typical and basic representation of smart classroom, having the teachers, also have people that they connect the internet, the technicians or system experts that are monitoring or organizing the teaching activities, and also kind of designing the system to work effectively. For example, people fixing the internet and also recording the classes, fixing any digital issues that may arise with the digital framework of the classroom. So also we have the teacher in the classroom, we have camera, also we have the sound system, we have headset and the projector. All these things just for basic, but China has moved beyond this level, and they also incorporate digital twin technologies in the classroom, where you see a different virtual laboratory and also using an advanced technology like humanoid robotics in teaching. So because of this system and the how our study is designed, the intersection of learner, teacher, and the technology, we propose a theory called ecosystem theory. This theory we use the concept, like biological concept of a known British scholar called Tansley in 1935, with the concept of the relationship between organisms and their environment. So in doing that, we want to show the relationship between the users of smart technology and also how they interact with the technology in either in learning or in delivering lectures as for teachers. So for a user or a student or a teacher to be able to have an adequate understanding of technology, smart education technology, the teacher also needs to be able to create an amenable relationship, try to understand the system, the workings, the mechanism that of the technology and how to use it in terms of instructional purposes. So for that, our study is being governed with a multiple case protocol, where we selected 5 provinces to analyze this. Though China has up to 34 provinces, including the 5 municipalities and regions, but we didn't also try to count Hong Kong at Taiwan, so avoid some political issues. But
Dear authors,
kind
this
of,
is a 10 minutes gentle reminder.
all right, just a minute, let me random. Okay, with that, we focused on 5 kind of prominent provinces in China. For example, in Jiangsu province, in the quest of digitize the school system in the province, they also initiated what we call the smart campus for high school, which it has its number here. For case of Hubei, so they also introduced what we call Millennium Plan in 2017. Case of Sichuan, they also introduced a digitized governance system in the school system, in the school in atmosphere or ecosystem. In the Beijing, which is the capital of China, one school called the Beijing Huiwen Middle School. So Beijing Huiwen Middle School also developed what we call Smart Huiwen Learning Platform, using the name of the school to design this learning platform. So with that, we have Guangzhou. Guangzhou tries to, that is Guangdong province, make use of big data to promote school governance as well. So with that, we try to see the role of this. The role of this policy is that it develop smart campuses and education, enhanced education services, also establish data-driven management platform for school, and the policies also has 3 C's, which is cooperation, content, and connection. So with that, the impact of this is that it transforms the educational landscape of China and also make it more seamless and effective for learning. So the challenges that we have, a couple of challenges like also, even though this policy has made remarkable achievement, but there's still challenges such as the teachers not quite conversant with the technology. There is still digital divide between urban city and rural schools in urban cities and the rural distance. So which the schools in rural area, they are still not quite okay with the technology. So there is kind of misunderstanding, disparity in that aspect. So financial constraints, especially schools in the rural areas. So in conclusion, having cited all these challenges and importance and achievements of this policy, but we said that our studies suggest key priorities for future development, targeted intervention to bridge urban and rural resource gap, and also robust ethical framework. There is this kind of ethical concern when it comes to using smart technologies and all that, and also comprehensive teacher support, like maybe teachers professional development training, especially for teachers at the rural area. We then thank you for your time, and then
yes, thank you, Enika, Ikena. This system is applied for primary or secondary school. How about the implementation on the rural area? Is that infrastructure is support in China, like 5G,
okay.
network, AI, like you mentioned just now?
Okay. I would say that for using this technology, China is also trying. They have identified them. This is a report, last 2 years report on the achievement of this policy. So they have identified that schools at the rural area are still finding it difficult. One is that not every school at the rural area has integrated, accepted this advanced technology, for learning. Based, for example, due to lack of knowledge, and then teachers at the rural area are part of China, they don't have that higher education level to be able to understand the mechanisms and the usability of advanced technology. So it's still a problem in the rural area. But the government is also trying to bridge that problem. So trying to take teachers from the city down to the rural area.
Okay, okay. means it's not implementation maybe in the city and maybe suburban. Yeah, rural area
Yes,
still improving the connectivity or infrastructure. Thank you. Yeah, thank you.
yes, thank you, Professor.
Thank you so much for the presentation. We are just left with one more presentation because he was not able to present in the previous session. So yeah, we have Misab Urham Siddiqui with the paper titled Non-Blocking Keystroke Dynamics, Authentication with Adaptive Learning and Fallback Verification Mechanisms. You may please go ahead with your presentation.
Okay, thank you, Anisha. I'm
Yeah.
going to share my screen.
Yeah, you can share your screen.
Is my screen visible?
Yes.
Okay. So thank you for giving me the opportunity to present in this session. Because of time difference, I was confused. Sorry for that. And I'm Ispaur Rahman. I'm presenting my paper, Non-Blocking Keystroke Dynamic Authentication with Adaptive Learning and Fallback Mechanism. As we know, the passwords are the ubiquitous way of authenticating the users throughout the world, as we are living in a digital age and we are accessing websites and applications where we need to get ourselves authenticated. And the mostly used method of authentication is the password. So we are always using passwords, and these passwords are vulnerable to many kind of attacks like phishing, brute force attack, shoulder surfing, and social engineering. For example, if we are sitting on a cafe and we are entering our password, so someone standing beside our standing nearby may see the password and can access our website or the digital resources or the website that we want to access. So it may get compromised. And similarly, brute force attacks or phishing through phishing can also the imposters or the hackers can access our account and they may steal the information that is stored on our systems and computers. So the compromised password lead to unauthorized access and data breaches. So we need a more robust authentication method that is just beyond the password. Here, I have proposed a new way of authenticating the user. Although the keystroke dynamics is not new, it has been introduced in early 1970s, but it has been still in development phase. Here we have introduced a new layer of security using keystroke dynamics. Here, this is since a behavioral biometric that analyzes unique typing patterns, and it's like a typing signature. Since when we go to banking institutions and we have to sign on the checks, and it's similar to that kind of method, we are typing our password. And since we know the password, and that's why we are fluent with typing the password. And if someone has already seen our password, but that person cannot be as fluent as the genuine user. So this metric is difficult for the imposters to replicate. And the key metrics that are used in keystroke dynamics are dwell time, that is how long a key is being held down. In the flight time, that is the time between releasing one key and pressing the next, and the overall typing rhythm and the cadence of the user. Our novel approach is like that the traditional systems that use keystroke dynamics for authentication, they simply allow the user or disallow. And in this case, if a genuine user is having stress or fatigue or a new device, maybe may not get the chance to log into the system or the log into website where the person want to access. But in our system, we are using a non-blocking approach, and as a the keystroke dynamics as a secondary layer of authentication. In normal systems, we just check password, Here, we are using the password first. And if the password is correct, then we analyze the typing pattern against a user's baseline stored in the database. And if there's a significant anomaly is detected, then we do not deny access. Rather, we ask the user to give some more credentials based on the registration. And this is the proposed workflow of the system. First is the enrollment phase, where the user, where we are collecting the typing data over multiple sessions to create a baseline profile for the user. And once the baseline profile is created for that user, then the second step is authentication. When the registered user want to get authenticated, that user enters the password, and in case the password is correct, then the keystroke data will be matched with the stored baseline profile. And if there's a difference in the baseline profile and the captured keystroke dynamics data, then the user will be asked for fallback verification mechanism will be activated. And in case the password is incorrect, then the user will be simply denied the access. So it is still secure as the password is secure, but it is also using the fallback mechanism in case of anomaly is detected in typing pattern. This is the diagram that is showing the overall system workflow and the fallback mechanism workflow. This is the fallback and adaptive learning method. In case of anomaly, the user will be asked for, say, one-time password may be asked, or some security questions may be there, and biometric verification can also be used for the fallback verification mechanism. The simplest one is the OTP that can be sent on the registered email or the mobile number. The security questions and biometric verifications can also be used as a fallback mechanism. The adaptive learning comes here. The system continuously learns from verified genuine sessions. For example, if one user is trying to log in and he has successfully logged in, then its typing behavior will be updated because the user is genuine. And in case some imposter is trying to log into the system, and the imposter is also having the password through any method, say for example shoulder surfing, and the imposter is trying to access the system, although the password is correct, but the imposter cannot match the typing behavior of the genuine user. So the system will ask for the fallback mechanism, verification mechanism, and the imposter will not be able to get the one-time password or the biometric verification or the security question. So it will prevent the incorrect, you can say, typing behavior of the user to be updated in the baseline profile. So in case of only genuine and successful verification of the session, the typing profile will be updated. And in case of imposter, the typing profile will not be updated. In our initial setup that I have used in the initial phase, we have collected data from 20 participants and over 2 to 4 weeks. And we have used the features mean and standard deviation of dwell time and flight times. And the classification model that I have used is dynamic time warping. And I have not used support vector machine, but it will be used in the next version of my application. And these things in the future version of the application, we will measure the false acceptance rate, that is the rate at which the imposter is being granted the access. This is the security issue. And false rejection rate, the rate at which the legitimate user is being challenged with the fallback mechanism. This is related to the usability of the system. And equal error rate, that is a key indicator of the overall security. So in conclusion, our non-blocking system provides a balance between security and user experience. The keystroke dynamic adds a powerful, hard to fake layer of security to traditional passwords. Since we are still using the password, so it is just an additional layer of security that will strengthen the security of the system, because the keystroke dynamics is hard for anybody to imitate as the genuine user. The adaptive learning component ensures the system remains effective over time, because we are updating the baseline profile of the user on successful login of the system. This research demonstrates that behavioral biometrics can significantly enhance modern authentication technologies. And in future work that I'm still working on, we will try to implement deep learning models and expand the data set to include more participants and different devices, because right now we have used only the laptops and desktops. We want to use mobile devices also in future version, or the next version. I'll try to implement that also, and explore integrating continuous authentication throughout the entire user session also. So this is the future work that I'm going to do. And thank you for patient listening.
Yes, Mitra, thank you for presentation. Some case, the tape also smart. They doing entering the keypad, the password also smart. Uh, in this case, how you system identify this genuine or original users, or tapping approaching to tap the password or the keypad, because we cannot say the behavior of a user, uh, the tapping, the scammer also very smart now. They do
Yeah.
like the original ones. So
Yeah, the scammers are
yeah,
also very smart.
yeah.
So I am using this as a secondary layer of authentication, since scammers are already there and they are trying to access the current systems that are using passwords. So I am just trying to add an additional layer that will stop these scammers from imitating the user's behavior just by getting the password. They need to imitate the typing behavior also. That is quite difficult.
Oh yeah, yeah. Okay, yeah, maybe as your future, may we use AI or smart system like all algorithms to detect the
Yes.
behavior. Oh, yeah, yeah.
Yeah. I'm going to work on these new algorithms on CNN and RNN also. But
All right.
that is my future work, and I'm going to implement all these algorithms also.
Okay, thank you. Thank you.
Okay, thank you, sir.
Thank you so much for the presentation.
Nisha, I have a question.
So with that, we
Okay.
have completed all our presentations for this session, and I sincerely thank all our authors for their presentation and contribution in this session, and all our participants for being a part of this international conference. I hope this session
Thank
was
you.
informative enough for you all. We, on behalf of the whole team, we thank you for your support during this 9th version and all the previous 8 versions of the conference, and we'll be happy to have you in the 10th version in 2026. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months, so kindly cooperate with the team of WS4 2025. I'd also like to thank our session chair, Professor Evizel Abdul Kadir. He has a small token of appreciation on behalf of the team of WS4, Global Knowledge Research Foundation, and partners. Thank you for your valuable presence, sir.
Yes, I would like to say thank you to committee. Usual is invite me for this conference as session chair. Thank you so much. Yeah.
Thank you so much, sir. Now I just request you all to please turn on your cameras for a quick snapshot of this virtual conference. Okay, thank you so much, everyone. Thank you. Take care. See you all soon.